Okay, good morning everyone, and today I am in a mood to chat. Uh, Early morning, weather is good, not feeling so too cold. Last 2 days had been terrible. I mean, terrible cold with the rain and all, and it was difficult. So, now tell me, uh, do you understand the analysis using mode superposition, response spectrum method using mode superposition? Anyone? The specific question that I want the answer to is the rate of convergence. Uh, it's a series superposition, series of summation series. So when we look for displacements, I mean, superposition can be for anything. It can be for displacement, it can be for bending moment, it can be for shear force, whatever. So the question that I am posing is, convergence of mode superposition. The response quantities we are looking at is displacements, and then obviously related to displacements we can have bending moments, and shear force. So essentially we can also have axial thrust or torsion, whatever, if required. So all of these are essentially what we refer to as stress resultants. Now why do I bring this? Displacements, obviously they they refer to the uh, serviceability and these are all the collapse limit states. Collapse is rather a dramatic word, I would rather say. Ultimate limit states. So these are the forces we normally design for these estimate these capacities and then demands, and then provide adequate capacities in the section so that we have sufficient margin of safety against these ultimate limit state failure limit states. and then we check whether the displacements are adequately constrained so that serviceability is not hampered. Now, a critical, I mean, this is fine as far as the basic design assumptions go. The problem with dynamic conditions and particularly earthquake analysis with using mode superposition is uh, displacements converge faster than stress resultants in mode superposition. Right, so that's a point that you can verify if you have not done so earlier. So what are the effects of this? Why should we be worried, or should we be worried at all about this fact that displacements converge faster than the stress resultants in mode superposition? The problem is the equivalent lateral force distribution for analysis using response spectrum is based on the displacement profile story displacements. Right, remember the forces that you work out in for the analysis. Right, so these are the lateral forces that you have. So let's say F1, F2, F3, F4. So these are the equivalent lateral forces. Determined from response spectrum analysis. Right, now there are two things here. So response spectrum analysis, first of all, it is based on this response spectrum analysis, and we eventually first estimate the displacements, and from the displacements we find out what are the spectral accelerations, and then model what are the shear force, story shears, and from there we compute these lateral forces. Right, so displacements obviously they converge very quickly, and we may be tempted to stop the mode superposition much earlier. But unfortunately, it is the forces that we are looking at, and the forces more so in the forces in the members that we are looking at, and those stress resultants in members, they converge much slowly, much at a much slower rate than the displacements, and higher modes contribute significantly to the member forces. So the first thing is contribution of higher modes is significant for in stress resultants. Stress resultants, I am talking of bending moment primarily and shear force. Now, this was realized, particularly, we know it is it converges much slowly, but nobody, it was not realized that it could be so important an issue until it was observed that in 1985 Mexico earthquake, several upper floor stories were damaged. Columns in several other upper floor stories of well-designed buildings got damaged during that earthquake. And then after it was, upper floor is again very unusual, because if you add up the shear force, tall standing vertical, almost in vertical cantilever kind of a system. So as you go on adding up the shear force actually increases towards the bottom, shear force and bending moment. So why should the failure happen at the top floors, towards the top? So after the careful analysis, reanalysis of the complete system, it was realized that the problem was because the contribution of higher modes of vibration, where you have larger curvatures, and leading to concentration of the stresses in upper floors, they were neglected, and because the upper floors were already they were designed for lower level of forces, so they had much lower capacity to accommodate this kind of omission. The lower down floors, because they were designed for higher capacities, so obviously they had more cushion to absorb this kind of error of omission, and that's how several upper floor stories sustained heavy damage during the 1985 Mexico earthquake. So that leads to the problem that contribution, how to account for this higher mode contribution, how to protect against this higher mode contribution. So that is done by typically by using dynamic amplification factor to account for higher modes in dynamic situation. Dynamic analysis. So whatever results you obtain using equivalent static lateral force analysis, uh, amplify that by a dynamic amplification factor, and that will account for the effect of higher modes in the stress resultants, and that value has to be taken for the design of columns. Now another thing, we need to do this dynamic amplification factor to ensure strong column and weak beam, right? So we are doing this only for the columns. So this dynamic amplification factor, we are doing this only for columns. Right now we are talking about the design of columns, design actions for columns. The idea is we need to provide for higher capacities in columns, and so that we do not allow any plastic hinge to form in columns. Uh, that's a very strong word. I mean, not allow any plastic hinge to form in columns. We do sometimes allow even columns to develop plastic hinges, particularly when the axial load on the column is very, very small. For example, if it is about the axial load compression, if the column carries net tension, then obviously it is acting as a vertical beam, and we can obviously afford to have uh, plastic deformation with curvatures, with sufficient curvature ductility that may be achievable, and then the detailing is also like a beam itself in vertical, in with vertical orientation. But not just for the tension. I mean, even if the axial load, axial compression is very small, even then we can allow about certain moment capacities to be reduced, and inelastic deformations to take place, hinging to take place in certain columns, provided that the axial loads coming onto the column, compression coming onto the column is very, very small. And but in no case we do not allow the flexural capacity, moment capacities of column to be less than uh, total moment capacity at any floor to be less than 10% of what is estimated from the elastic analysis, and then the amplification. So that's the case. So now the issue is So one thing is dynamic amplification. So column moments have to be amplified by dynamic amplification factor. So MCU, ultimate moment in columns, can be of the order of as large as 2 times moment elastic moment capacities that are predicted, right? So this is what uh, dynamic amplification and overstrength. Remember, we had mentioned that there is an possibility of overstrength in the beams, and we need to account for overstrength in beams in while deciding the capacity of the columns. Column capacity has to be more than the capacity of the beams, including overstrength. So if we combine the dynamic amplification and overstrength factor, that factor approximately comes out to about 2 times the elastic moment. It slightly it varies from 1.5 to about 2. So 2 is a conservative estimate, but the actual number will be somewhere in between 1.5 to 2. So that needs to be done. And another thing is that uh, because the ultimate capacity, this maximum moment will not happen at the both ends simultaneously, right? So this maximum moment does not occur simultaneously at both ends. Of the column, right? So let's say so this is the clear span. Let's say this is depth of the beam. This is also the depth of the beam, and this is, let's say, clear span of the column. Now, so at this end and at this end, this maximum moment capacity that we have determined, uh, I mean the maxima, this ultimate including dynamic magnification, will not happen simultaneously. I mean it cannot be that this end will also be subjected to this whatever the maximum moment is expected here, and this end will also be subjected to the maximum moment that is expected here. At the same instant of time, both of these maxima will happen. The implications are in the calculation of the shear force in the column. What is the maximum shear that will happen, right? So the implication is that whatever the ultimate shear capacity is, the maximum shear force and maximum moment doesn't occur at the same time. So another issue is that we need to take care is what so another one thing that I need to record: maximum column moments and maximum column shears. Do not occur at the same time instant. Right? So it is not right to consider the maximum moments at the both ends acting simultaneously and finding out whatever is the uh, actual maximum shear, and then account for that in calculating the moment capacities. Why that shear is important? Because in your analysis, uh, let me draw this. That's another thing that you need to take care. Analytical models are based on center lines. Nodes are placed at the intersection of center lines. Right? So whatever moments that you are calculating, moments and shear force that you are calculating, those are calculated at this center line, center point. This is the node. Right? So this is the node, this is the node. While it's obviously deep within the beam column joint, while you are designing your column capacity at this level, at the face of beam column joint. So the column capacities, beam capacities, column capacities, they are to be determined at this point at the face. So whatever is the maximum moment that you are doing here, it has to be reduced by some amount to find out what is this maximum moment at the base of the column, right? And base of the column at the top of the beam, top level of the beam, or at the soffit of the beam, as it is known. So how do we do this? So one thing is this is MCU. So MCU would be taken as twice ME minus about we would take 60% of the shear force, ultimate shear force acting on that, and 0.5 times D times the shear force. So whatever is the column, I mean these are the shear forces. So depth of the beam is D, so this is D by 2, so that's 0.5 times D. So this is the moment that needs to be uh, taken off from the maximum moment capacity that we have estimated at these nodal points, that is intersection at the uh, center line model. And we assume that when we have this maximum moment, the shear force, maximum shear force, I mean at say conservative, that total maximum shear force would be about acting about 60%, and that needs to be taken off. So that will reduce the moment at the beam column junction at a level of about twice elastic moment minus 0.3 times beam depth multiplied by the ultimate shear that we compute. And what should be the ultimate shear? The ultimate shear would again be, let's say, dynamic magnification factor would again be about 1.8 to 1.9 times V elastic. So this is again dynamic magnification factor. Right? Or we can also work out the on the basis of the elastic moment, what is the total moment here at this end and what is the total moment here at this I mean moment that is calculated, and then find out what is the uh, uh, sum of the two moments. I mean just like we have in the case of uh, right. So based on this we can find out what should be the shear force. So this will be the moment A, moment B, and V is equal to MA plus MB divided by L, if this is L. So in this case L would be based on the I mean we'll need to look at what is the moment at this end, I mean, and at this face, and what is the L is clear span, and then work out what is the moment. And again this moment has to take into account the dynamic magnification factor, total magnification in the maximum moment that will happen in the case of dynamic situation. So the static analysis, linear elastic analysis based on equivalent static loads, lateral loads, that has to be magnified by about again 1.8 to 1.9 times. Simple figure is 2. That can work, and that will take care of the dynamic magnification of the dynamic magnification in the columns. And this shear we assume it operates at the 60% when the maximum moment we are computing the moment capacities, so that from we can transfer the moment capacities computed at this intersection of the center lines to the face of the column uh, at the face of the junction, and that is where the maximum capacities are determined, and appropriate reinforcement detailing has to be provided. In the case flexural reinforcement has to be provided according to these moment capacities and for these shear maximum shear. And as I said, in in case axial load is very small, I mean we accommodate all the shear force in the beams up to that level coming from the top, and accommodate add all of that, and that provides the axial force due to earthquake effects, and that is to be added to the axial loads coming from the gravity load, and that will determine what is the total axial load capacity uh, that is required in the case of columns. And if that axial load is very small, then it is possible to allow for some inelastic deformation in that column, but total moment capacity reduction in a column at any level should not be uh, should not lead to anything less than 10% reduction in total moment capacity as predicted from an elastic analysis, right? So that is a restriction on the possible distribution and reduction of moment capacities in the column, but generally we do not it is better not to uh, allow any inelastic deformation to take place except at the bottom of the uh, columns and at the support levels, at the ground floor support levels. That is where there is no other element to dissipate energy, and the columns have to develop hinges, and appropriately you need to account for spatial detailing, ductile detailing, so that large curvature ductility can be achieved at the bottom of the uh, end, and also at the it is possible to have it at the top level, because there is no axial load in the top floor columns, so you can we can allow to for the inelastic deformation and curvature ductility can be achieved in the top floor columns. So except at these two locations, the columns in general should not develop hinges, and that can be achieved if we uh, make provision for the overstrength of beams, and also for the dynamic amplification of the stress resultants during mode superposition, dynamic analysis, and use that for our design. So rest of the provisions are more or less, I mean the minimum reinforcement, maximum reinforcement, those are governed by the uh, ease of construction and compaction related issues. The concrete has to uh, be, it has to be, it should facilitate compaction, so we do not allow uh, very heavy crowding of reinforcement, which will hinder flow of concrete around the reinforcement bars. So longitudinal reinforcement, they are uh, about I mean the usual maximum limit of the reinforcement detailing, longitudinal reinforcement, and that is usually we don't even reach that maximum limit because of the requirement to have stout columns. It will be it's impossible to have a very slender or very thin section of columns coming up in seismically active region because of the drift considerations. So there is a limit on the acceptable drift, and from that acceptable drift consideration, the column dimensions are anyway going to be very large to achieve sufficient stiffness. And when we have such a large cross section of columns, the reinforcement, longitudinal reinforcement that will be required to withstand these moments will be much smaller than the maximum uh, allowable longitudinal reinforcement in columns. And the usual, I mean, guidelines for splicing of reinforcements, they apply. I mean, we cannot curtail reinforcement more than 50% of reinforcement at the same place. So it has to be staggered, and so that we can, and of course, it has to be avoided in the plastic hinge region wherever there is a plastic hinge coming up in the frame, in the column or beam. So uh, now that comes to another. So beams are, we discussed about seismic design of beams, we discussed about the seismic issues in design of columns. Now that leaves us with the issue of beam column junction, this critical beam column joint. What is special about this beam column joint? First thing is, we are providing, if you pay attention, we are providing the moment capacities at this end, at the column face, beam column face. We are providing the column capacities at this beam column face. So what happens to the joint? And we also allow the reinforcement in the beam to yield. So longitudinal reinforcement, when we are looking at the ultimate behavior of the beam column joint, the maximum most critical situation would be when the beams have already yielded. So both ends, I mean in this case, both beam ends, the reinforcement has already yielded. So what happens in that case? So beam column, so let me draw this figure. Right? So this is the center line. And in case of beam reinforcement, so let's say this is the beam reinforcement. So this is beam reinforcement, and this has already yielded. it goes across the beam column joint, and this has already yielded. So let's say this is AS1 and AS2. So the force here is, I would say, for some if I can say that this is the force, if it has yielded, then AS1 multiplied by Fy, and this is AS2 multiplied by Fy. And then there are forces of the columns. So let's say this is the shear force, let's say this is H. So total shear, if we can say, uh, in the junction joint is horizontal shear in beam column joint due to earthquake is equal to AS1 multiplied by Fy plus, that is the shear force, minus AS2 Fy. Right, so that is the okay. AS2 will of course be equilibrating. So that is the total shear force. So this will be the equilibrating forces. So now this panel zone, this is what we call as the panel zone. This is under the shear force like this, under the shear like this. And this is the behavior that you will see in this is more critical, critical portion, critical element of design in case of steel buildings. So this panel zone behavior is very critical, that it has to be adhered to. I mean, this is the additional, this is the shear force, it is under influence, and it is under compression, and tension we disregard in case of, at least in the case of concrete. So this compression strength, there is massive compressive stress because of the shear in this beam column junction, and this has to be resisted by adequate capacities have to be provided for these shear reinforcements, for this to take care of these shear stresses. And this is done by continuing the transverse reinforcement in the panel in the beam column junction in case of reinforced concrete structure, and in case of steel structures special details are required for the to ensure that this panel zone doesn't buckle under this compression, this massive compression, and that is often the cause of failure of steel buildings. and we need to provide for this protection against this uh, beam column junction in reinforced concrete as well as steel buildings. So how we do that, we will discuss in our next lecture, that is tomorrow, and we will also follow it up with discussion of shear walls. How do we design for shear walls and how do we provide them? How do we integrate shear walls with the rest of the building frame, and so on. After that, next week, I'll try to rush through some of the special, most of the considerations that we have dealt with in the discussion of seismic behavior and seismic design of reinforced concrete frames. The basic issues, philosophical issues are same, even with the steel frames. It's only the material which is different. So just as we have special provisions to achieve large curvature ductility for reinforced concrete frames to ensure ductile behavior, there are similar provisions which actually enhance the behavior of the steel frames. See, the steel as a material being ductile isn't helpful if the structural behavior as a whole is not properly designed to control the behavior as we want it to behave. For example, we don't want this panel zone to get to buckle in the case of in the event of seismic loading. If this panel zone buckles, then everything is gone. So we need to ensure that we have sufficient capacities, and how to achieve that, so that we will try to uh, rush through those basic provisions, basic guidelines, and that will be the end of this course, hopefully next week. So, any questions?
Sir,
Yep.
sir, in the previous slide, please explain that MCU, that 60% subtraction of that shear moment.
Okay. uh, you mean this, right?
Yes, sir.
So,
On which phase? It is on center line, it is
no,
decreasing, or where it is decreasing?
center line is what we compute this one, right? So this is what happens
Yes,
at
sir.
the center line, but what we need is at the face, right? So we need the moment capacities at this
Yes, sir.
level, right? So this obviously has to be reduced by this half of the lever arm. This, so if this is the shear force, then this moment would be V times half of D. So that is what this is, right? Now we also assume that this V is
Yes,
not
sir.
acting at the full value when we are looking at this maximum response, maximum moment. So we assume
Yes.
that it is acting at 60% of its maximum. So that comes out to about zero point 0.3 times dV. And this V is the ultimate shear force, that is again based on elastic forces that we compute and multiplied by overstrength factor and the dynamic amplification factor. So total is again roughly 1.8 to 1.9.
Yes, sir.
Right? So any other question? Okay, fine. So we'll meet tomorrow at 10 again, and hopefully I'll not be uh, in a I'll not be constrained to postpone it any further. So let's hope we will be able to meet our date tomorrow at 10. Thank you.